Hello, welcome to our webinar, Understanding and Mitigating AC Interference for Co-Located Pipelines. This is part 4, which will focus on monitoring. I am here to introduce you to Alex Rodriguez, who will be presenting today, and Andy Florence, who will also be assisting with questions. I'm Anna Wilson, Marketing Manager for American Innovations.
Well, good morning, Anna. Thank you for the introductions. My name's Andy Florence. I'm the Director of Pipeline Integrity Management Services for American Innovations. Been in this role for about 9 years now and have enjoyed every moment of it. I enjoy the mission. I understand clearly that when I wake up in the morning, my job is to help our pipeline operators deliver energy safely to safely to the consumers. So every time I turn on the thermostat and I crank up the heat, or I turn on the AC, I know I've played an important role in that process. So it's a good feeling. Alex Rodriguez, my colleague, is in Austin, Texas. By the way, I'm in Denver. Alex is down in Austin, Texas. He's the product manager for our remote monitoring unit. And as we'll discuss later, monitoring your potential AC interference on your pipeline is a growing concern. And he's going to give you some tools to help you mitigate this threat to your pipelines. Alex, if you would, next slide, please. Thank you. As Anna mentioned earlier, this is part 4 of a 4-part webinar series. I want to thank all of you for taking time out of your busy schedules to spend an hour with us and talk about AC interference. It is a good time to be in the pipeline industry. A lot of metal going in the ground, a lot of charged energy going up in the air. So this is a timely discussion and a timely presentation. Alex, if you would, please. Our first webinar series was there you go. Our first webinar was on AC interference. We gave you a definition of AC interference, and we also told you what to look for when you had your ditch open, your pipe exposed. What are the symptoms and characteristics of AC interference? So we gave you a definition, and we told you what to look for out in the field, out on the right of way. Webinar number 2, about 6 weeks ago, was okay. We told you what the problem is, and we also characterized that problem as a multi-headed monster. Different types of AC interference can impact your pipeline, pose a threat to your pipeline and your people. It's also dynamic and it's elusive. One day it's there, the next day it's not. So it's a really hard problem to solve. The analogy we used was this multi-headed monster. Webinar number 2 was, all right, we're going to tell you that you're never going to be able to slay or kill this monster, but we're going to give you some weapons in your armory, some tools in your toolbox that will allow you to control and mitigate and to tame this monster out there. And that was webinar number 2. What are the tools in my toolbox to control this monster? Webinar number 3 was 2 weeks ago, and that was my presentation. And you might say, well, if I've got a small segment of pipe that's co-located in a power line and a utility corridor, I don't really need, I probably know everything I need to control or to mitigate AC interference. But what if you're a pipeline operator with 12,000 miles of pipe spread across multiple geographic regions, different operating parameters, different size of diameter pipes, different types of crossings, electrical power line crossings? Where do you start? You probably don't have the resources and the time to attack this multi-headed monster all at one time. So webinar number 3 was to give you a logical, defensible, risk-based approach to help you efficiently allocate your resources and to start attacking this monster. We walked you through some of the risk factors. We gave you a framework for assessing risk along your pipeline and helping you prioritize where your pipe might be exposed to AC interference. And then he laid the foundation for a program that allows you over the course of time to continually assess and to continually address this problem of AC interference. Today's topic is an integral, important concept, not a concept. It's actually one of the more important weapons in your armory or tools in your toolkit to keep this monster at bay, and that's monitoring. And that's where Alex comes into play. Alex is going to talk about monitoring strategies and some of the tools that we offer as well to help you keep a pulse and keep tabs on this multi-headed monster. Alex, if you would, please. So let's start reset. For those of you who joined the first webinar, this is the definition of AC interference. This definition comes from a report from INGA. INGA stands for the Interstate Natural Gas Association of America, which is a consortium of pipeline operators and production operators who commissioned a report to canvass all of the documentation that is out in the industry around AC interference and to consolidate that into one report. They did a really, really good job. If you haven't read this report, I strongly recommend you go out and you download it and you read it. It's about 122 pages. It gives you some really good guidance. It gives you a really great definition, what you see here, but also gives you some great criteria for assessing and quantifying AC interference, as well as talking about program management, things like that. You got to feel a little bit sorry for the guys who were tasked with this project. There's a lot of documentation out there. Some of the earliest documentation that I've read goes back to the 1980s. So having to read all of that documentation, all those technical journals and technical papers, and bring that into one concise document it was quite a challenge. And so kudos to these guys who did this project and came up with this document. The definition you see there, that's the definition they provide. In layman's terms, it's real simple. If you're out on the right of way and you look up and you see a power line overhead and you look down and you see your pipeline or an above ground pipeline marker, the first thing that should come to mind is, I might have energy being induced on my pipeline, which causes a threat to my asset, my pipeline, and also a threat to to the public and my personnel. So it's a really good definition to start with. Now we understand what AC interference is, the definition. Alex, if you don't mind. Next slide. So the question you really have to ask then is, do I have a problem? AC interference is a known phenomenon that started, documentation goes back to the early 80s. Why is it a topic of concern? Why is it getting so much attention these days? So let's take a look at a few maps here. This first map you see here is all of the crude and refined product transmission pipelines in the United States. Again, these are just jurisdictional pipelines, transmission only. This does not include gathering lines and other shorter flow lines and things like that. So these are the transmission pipelines in the United States. It makes sense, right? A lot of concentrated pipelines in the shale plays out in the Permian Basin out there in West Texas and New Mexico. A lot of pipelines up around Cushing in Oklahoma. So we're transporting our product from the field to central processing locations for storage and for refineries down on the coast out there. Not a terribly complex pipeline network, and mostly located out in the Midwest and the West out there. Alex, next slide. Now let's take a look at our natural gas transmission system. Again, this is natural gas transmission, jurisdictional pipeline only. This is not gathering lines or flow lines or distribution lines. Much more complex network and a much broader network of pipelines. A lot of metal in the ground, right? Makes sense, right? We're taking, when we're processing natural gas or producing natural gas, we don't have to take it out to a central processing place like refineries on the West Coast. We actually scrub that gas out in the field before we put it into the trunk line, and then the trunk lines take it out to the city gates. So I'm going directly to the end consumers, and there's no intermediate process of having to create refined products out there. So much more complex network, much broader scope, spread across the entire United States. So we've got a lot of metal in the ground. Alex, if you would, next please. Let's take a look at the electric transmission system now. So makes sense too, right? Everybody knows urbanization or U.S. population is concentrated largely on the East Coast, but we're migrating west. So we see a lot of electrical transmission lines out on the East Coast, and it's becoming thinner and becoming less dense as you move to the east. Of course, and out in California, a highly populated area, you see a concentration of electrical power lines out there as well. So now we bring it all together into one single map. We see a lot of intersects. We see a lot of crossings. We see a lot of charged metal in the air and a lot of natural conductor metal in the ground out there. So the opportunity for AC interference is, while it is a well-known and documented phenomenon, has been around for a while, just the population growth and the expansion of the U.S. and our development as a society leads us to the conclusion that AC interference is becoming a more common problem. All of your old engineers and pipeline engineers who used to work out in the West Coast, where you putting your crude lines in, and there wasn't a whole lot of electrical transmission power lines out there, probably didn't see AC interference 20, 30, 40 years ago. But your younger pipeline engineers, as we become a more urbanized society, access to land becomes harder, and we have to share our right-of-ways with other utilities. AC interference is a growing concern. And so, do you have a problem? It's crowded, and more than likely, you do have a problem, and this is a problem that you need to be aware of as you're out there on the right-of-way. So with that, I'm going to hand it over. I've set the stage. I've gave you a definition. I've told you, I've kind of put the fear of God in you. I hope you probably do have a problem. And with that, I'm going to hand it over to Alex and let him pick it up from here, and I'll be back at the end to wrap things up.
Well, thank you, Andy, for the great setup here to this presentation, and thank you, Anna, for the great introduction. And I also want to thank the audience for as Andy mentioned, taking time to come listen to us today. A lot of us here at American Innovations have a real passion for educating, so anytime that we have an opportunity to teach about hot topics in the industry and teach you about technologies that you can use to solve your problems, we're really grateful when people come listen to us. All right, so before we get into the meat of this presentation, I do want to set the stage a little bit further with just some of the basic principles about how you can get AC on your pipeline. This is covered more in depth if you listen to our first webinar where Clay covers this information. And if you're interested in learning more about any of the other topics, please do listen to parts 1 through 3 of our webinar series just to really beef up your knowledge about AC interference. So one of the ways that you can get AC on your pipeline is going to be through this capacitive coupling. This generally occurs when the pipeline is waiting to be installed and is on skids nearby a high voltage AC line. Now, electrically, a capacitor is made out of 2 metal plates separated by some dielectric material. And that's essentially what's happening here in this scenario. You have your high voltage AC lines and your pipeline acting as the metal plates, and air is going to be your dielectric. So over time, there's going to be a charge built on this pipeline. And you can see in this image to the right, measurement was taken off of this, and you can see it has about 15.7 volts of AC on it. Now, this generally isn't going to be a huge risk in terms of corrosion on the pipeline itself, because it's usually just here in this type of scenario for a short period of time until it's installed. Once it's installed, this problem goes away. The big risk here is going to be to any personnel who's working nearby the pipeline, where any energy that's stored on it can discharge onto people. Fortunately, this is a very easy problem to mitigate. You just need to get a metal rod, drive it into the ground, and that's going to be your grounding rod, and then go to your truck and get some jumper cables and just make a connection between the pipeline and that grounding rod. And any energy that you have stored on this pipeline is going to get diverted into ground. Once you bury that pipeline, your risk of capacitive coupling goes away. But now you introduce a scenario for a couple of other problems, one of which is resistive coupling. So the pipeline is going to share a conductive path to the grounding systems of high voltage AC lines. Now, electric companies, when they're setting up these high voltage AC lines, they're designed in such a way to be able to handle abnormal activities that cause an excess energy to build on their power lines, and they're going to divert any of that excess energy to ground. Because your pipeline is in the ground in close proximity to that power line, you have that conductive path. That soil has a certain amount of conductivity. That conductivity, the higher the conductivity, the lower the soil resistivity. So that's one of the points that you're going to need to gather. Now, let's say you have an event like a lightning strike. Those AC towers are going to get any excess energy and just divert it to ground to get it off of their systems. And I mean, we do similar things in our industry. What do you do if you have too much pressure built up on the pipeline? Well, every once in a while, you're going to have pressure relief valves just to make sure that you don't put the pipeline in a condition where it can be in a dangerous situation. Electric companies are doing the same thing. Any excess energy that they have on their power lines, they're going to find a way to get rid of it. Unfortunately for us, it's going to ground where a pipeline is, and so then you can get that energy onto your pipeline. And because these are pretty random events, you can't predict when they're going to happen, and they can very often be of a high magnitude, you could create disbondment in your pipeline coating. You can create holidays onto the pipeline. You can have rapid forms of AC corrosion, but most importantly, it's going to be a risk to any personnel that is working on any above ground appurtenances whenever one of these events happen. So what do you do to prevent this? I mean, you can't really prevent it, but you can at least take the proper precautions to make sure that everyone is safe whenever they're working on the pipelines. Clay, in our second presentation, talks about the mitigation tools available. One of them is those gradient control mats. And setting up those things on any type of asset that an operator is going to be working on is crucial, because then you'll mitigate the chance for any step-touch potentials, which can lead to a shock hazard to any personnel. So lightning strikes is one way that you can get this resistive coupling. Whenever you have these high voltage AC towers, structurally fail, then you'll have a lot of short circuits. You can have an energy surge, which can also make it onto your pipeline. Now, you don't have to worry about Godzilla attacks too much here in the United States. That's mainly a problem for your Japanese counterparts, but you definitely should be concerned about what happens during major storms where things like this can occur. So again, hard to predict. Just make sure you have the proper precautions in place to protect any of the people that you have out there. Whenever we're talking about AC interference, for the most part, we're going to be talking about this inductive coupling. High voltage AC lines, as the name would indicate, have a high voltage associated to them, going up to 400,000 volts. And all of this energy is going to create a magnetic field, which can couple onto a pipeline that's underground. Even though there's quite a bit of separation between them, it's just so powerful, it's going to put some amount of voltage on your pipeline. Now, where have you seen a similar circuit like what's happening here? Think about that rectifier that you have. You have a primary side, which usually has a higher voltage, and then you have a secondary, which steps down the voltage to something else. There's no physical connection between the primary and the secondary. It's all just energy coupled on electromagnetically from one side to another. That's exactly what's happening in this scenario. By having a pipeline in close proximity to these high voltage AC lines, you've created a very large but very inefficient transformer. And that energy can go along through the length of the pipeline. Now, as Andy mentioned, ACI is that multi-headed monster that you're never going to be able to kill, but you can certainly mitigate against. You can certainly tame that beast. So NACE has some guidelines about what you can do as an organization to make sure that you're properly taking care of this AC threat. and they've outlined it into 4 parts. There's the analysis section, which is also like your risk assessment, which Andy spoke to in webinar 3. There's those mitigation strategies that Clay spoke to in our second webinar. And we're going to be focusing today on the monitoring strategies and the monitoring tools that you have available to make sure that you're keeping this monster tame. So first and foremost, one of the tools available to you is going to be coupon test stations. There's 2 parts to this type of device. You have the coupon, which is a series of metal slugs machined to a very exact size and made of a material similar to that of the pipeline, which is going to be buried underground. All of these are going to be installed in relative close proximity to the pipeline itself, because you're going to want to simulate what the conditions of the pipeline are at a specific point. Now, above ground, you're going to have the test head, which is pictured here. This is going to be your access point into that section of the pipeline. From the test head, you can take all of the measurements you need to not only check your ACI threat, but you can also check to see whether or not you're applying enough cathodic protection at a certain area. You're also going to want to have some sort of digital voltmeter. The Allegro has one built in, which you can use to take all of the measurements that you need from the coupon test station and capture any notes that you have in the field so that you can always reference them in the future whenever you need to see how this threat is progressing over time. And then you have your remote monitors. Pictured here is the Bullhorn RM4210, specifically designed for monitoring AC interference. This device, when used in conjunction with coupon test stations, can automate a lot of the readings for you. That way you can take everything from the comfort of your office or any web-enabled device that you have, and you can always stay on top of your AC threat. Let's talk a little bit more about the coupons. So there's a variety of coupons out there in a variety of different sizes. Pictured here is the Triton triple coupon that we have. So it has 3 coupons. Those 2 larger ones, those 2 metal pieces that you see there, are going to be for checking the effectiveness of your cathodic protection system. So one of them is designed to be connected to your cathodic protection. The other one is supposed to be your native coupon. So that one does not have any cathodic protection. You're just seeing how it's reacting in a certain environment. At the end there, it has a reference cell, which you can use to take your pipe to soil measurements from these coupons and also get your instant offs from the coupon. For the purposes of this presentation, we're going to be focusing on that smaller 1 centimeter squared AC coupon. And research has shown that the best size to most accurately gauge the risk of AC corrosion is going to be using that smaller coupon, 1 centimeter to 3 centimeters squared. And we're going to talk a little bit about why that size is important. And it has a lot to do with the sizes of the holidays. Now, these things are supposed to be simulating what would be if you had a holiday on your pipeline. Now, we're not going to be talking about the good type of holidays. We're going to be talking about the kinds of holidays that we like to talk about in this industry, which are just those anomalies in the pipeline, or sorry, defects in the pipeline coding. Now, the situation that has developed over the past several years is that technologies for pipeline coding have become really, really good. So this has been great for our DC systems, right, where we have to worry less about how much cathodic protection we apply on our pipelines to ensure that we're not getting any corrosion related to our DC. Now, unfortunately, for us, because these pipeline coatings are so good, anytime you do get holidays, they're not going to be that big. They're generally going to be small. And this is a problem for us because of our spread resistance. Imagine if you had a chunk of bare metal installed all along your system. Now, it's going to be a nightmare for your cathodic protection because you're going to have to crank that rectifier up really high. You're going to be burning through anodes really quickly, but you're probably not going to have that big of an AC problem, because any AC that gets onto your pipeline is going to be dissipated over the entire surface area of that exposed metal. So at any given area that you were to look at the current density is going to be relatively low. Now again, let's look back at that pipeline that has the great coating. You're going to have only very, very small holidays. So any AC current that you have on that pipeline is going to focus onto those small little areas, and that's where you're going to get that aggressive form of AC corrosion, which can cause, holes in your pipeline, which can lead to ruptures and explosion and all that bad stuff that you can imagine. The analogy that I always like to give about this when thinking about how the AC current density works is, imagine you're trying to burn a hole through a piece of paper using a magnifying glass, and you're out in the hot sun and you have your magnifying glass 4 or 5 feet away from the paper. Well, all of that light is just going to dissipate over a very, very large surface area, and there's not going to be a lot of heat at any given point. But as soon as you start moving that glass closer to the paper and you start getting that really fine focal point, you know exactly what's going to happen, because I'm sure we've all done it before. You're going to get a lot of heat at one point. It's going to burn a hole through that piece of paper, and then everything's going to catch on fire. So hopefully that never happens with our pipelines, but that's exactly what we're trying to prevent. So that coupon that we have, that 1 centimeter squared coupon, is going to represent the worst case scenario, because coupon test stations are not actually taking a measurement off of your pipeline. It's simulating what the conditions are like at a certain area. So you want to get a good idea of what the worst case scenarios are like, so that you can take a very conservative approach, or I don't know if I'd say conservative, but you want to take an accurate approach to how you mitigate your AC. You want to make sure that you know what the worst case scenarios are, so that you can take the appropriate actions. Now, when we're installing these coupon test stations and coupons, you're going to want to install those coupons in a vertical position. They're going to be roughly 6 to 12 inches away from the pipeline at the 5 to 7 o'clock position. Now, because those coupon test stations also have a lot of other connections, you can have your structure connections onto the pipeline, and you can have your zinc anode connections connected to there as well, and you can always take those measurements at a later time. Yeah. As far as installing that coupon, it's very important to backfill it with that native material. As I mentioned, we want to simulate what the conditions are like for a specific region of the pipeline. So you want to make sure to use the same type of soil that's surrounding the pipeline itself, and you want to use an air temp to make sure that those coupons are making good contact with that soil, so you can get the most accurate representation of what can be occurring out there. Now, these are some best practices, information to capture and install. And believe me, we've had a lot of calls with customers, and if you were to capture this information, it's going to save you a lot of time in the future, because you never really remember what exactly happened in an install 3 or 4 years down the road. It could have been somebody else who installed it. So definitely set up some structures within your organization to have this record keeping, and keep track of what exactly is out there, so that you can know why a situation is occurring, if it is occurring. So some important things to capture are going to be your GPS coordinates, any location name. This is very often company specific. Everyone has their own nomenclature or their own practices, so just capture whatever name you've given that location. The pipeline milepost number is another great point to look at. Backfill type, this is especially good as a check to see whether or not you've installed that coupon correctly. Calibrated measurement, and by calibrated measurement, I mean a comparison between the stationary reference cell that's installed with the coupon in comparison with a freshly prepared sample at the surface. Installed coupon orientation, again, this is another good check to make sure that you've installed that coupon correctly. And be sure to note the coupon size. So depending on who you buy your coupons from, we offer several different versions of coupons, so it's not always going to be that 100 centimeter squared and that 1 centimeter squared AC coupons. There's several options available depending on how you see the coupon should be set up for the conditions that you're trying to test. And different manufacturers have their own coupon sizes as well. And if you're going to be trying to calculate a current density measurement from a measured current, you're going to need to know that coupon size, because you're going to have to multiply that number by a certain factor to get that current density. And if you don't know what that number is, you can never really be certain what your current density is going to be for a specific coupon. So be sure to note that down. And then there's all of the readings that you can take off of a test head. And we'll go into these specifically on how to take them in the next slide. Okay, so one measurement that you can take using the Triton triple coupon is going to be your DC on potential. So you're going to set your voltmeter set to the millivolt DC setting. You're going to have your positive lead on the test coupon, your negative lead on the reference electrode, and then just capture that observed measurement. Okay. Your instant off potential, you keep your leads in the same position. You're going to toggle the switch that's on the test head, and this is going to break the connection to the pipeline. And instantly after you toggle that switch, you're going to look at your multimeter, whatever tool you have out there. And that value that you observe immediately after you toggle that switch is going to be your instant off value. You can do a spot check if you just untoggle the switch, let it get back to its steady state, toggle it again, capture your measurement. You can use that as your instant off value. Your native state or depolarized potential, you're going to have your positive lead on the native coupon, negative lead on the reference electrode, and then just capture that observed measurement from your multimeter. For the DC current, you're going to switch the multimeter settings to measure milliamps DC, get your positive lead on the test coupon, negative lead on the structure, toggle the switch, and then just write down that observed value. If you're going to want to get your DC current density based off of the coupon size, as I mentioned, that's going to depend on the coupon size that you have. If you're using those 100 centimeter squared coupons, for example, I believe you'll multiply it by 0.1 to get from your current density to amps per meter squared. For your AC potential, you're going to switch your multimeter to do your AC measurements, your AC volts, have your positive lead on the test coupon, negative lead on the reference electrode, capture that measurement. AC current, again, milliamps, AC, have your positive lead on the structure, negative lead on the AC coupon, toggle that switch, and capture that measurement. Going from your AC current to your AC current density, again, is going to depend on your coupon. If you're using the 1 centimeter squared coupon, you'll multiply that AC current value that you have by 1,000 to get to the amps per meter squared. Now let's talk a little bit about where to install these test points. One of the first things that I'd like to talk about is going to be looking at those inflection points. And by inflection points, I mean changes from where the high voltage AC lines converge or diverge away from the pipeline, and then they settle in a steady state direction, or that your pipeline may be doing. So take a second to look here at this illustration and see if you can figure out how many test point installations we would install here. Just take a mental note or write it down somewhere, and we'll discuss this and see if you got it right. So that first one, we see that the high voltage AC lines come closer to your pipeline, and then they level off and then start running parallel. So with that place where you have that change in direction is one inflection point. So that's a good candidate for you to install a coupon test station. We see that happening a little bit further down. You have your pipeline, which is now getting further away from your power line, so it's changing that direction. It's another good candidate for you to have a coupon test station. And again, it happens a little bit later in the pipeline. Another inflection point, it changed direction, so it's going away, kind of leveled off again, running kind of parallel to that high voltage AC lines. Now this one does happen a little bit further away, and you may be wondering, well, how far of an area do I need to pay attention to? What's my area of influence for these high voltage AC lines? And that's going to be a classic BAS, it depends type of answer. It's going to depend on the load that's on those high voltage AC lines. So if there's a lot of power running on those voltage lines, that area of influence is going to be greater. It's also going to depend on your soil resistivity. So the lower the soil resistivity, the higher the conductivity, and the more easily energy can flow through the soil and onto your pipeline. Now, there's not an exact number that I can give you. It's going to depend from every situation to situation, but some of the literature out there says you should consider any area within 2,500 feet in either direction, so that's about half a mile, as something you can check for as your area of influence. So there's 3 inflection points out there. How many people got 3? How many people got 4? Yeah, so you need to look up every once in a while. Sometimes the power companies will do something called transposition, where they change the position of the power lines from one location to another, and they do this for load balancing or to remove the inductive effects from one of the lines to the other lines and balance everything out. But this is another inflection point with regard to our pipeline. So you want to look up, see what's going on up in those towers and see if there's any transposition going on. They may call it rolling the lines, and that would be another good candidate for you to install a test station. Now, NACE SP 21424 also gives some guidance about where you should install test points. Now, anywhere where AC voltage is shown by calculations or by AC voltage surveys to be significant is an area where you'll want to have a test station. So anywhere where you know there's an AC problem, definitely install the test station out there. Any location where the soil resistivity is low. What's a low soil resistivity? Well, according to both the INGA and this specification, it's anything less than 2,500 ohms centimeter. Anywhere where the CP condition can be excessive. So look to see where you have your CP current sources and install another test station nearby. If you've done an inline inspection and you've seen that there's a problem or there's been a leak in a certain area before, install a coupon test station. You want to make sure that this problem is not being caused by AC. And if it is, then at least you can account for it and prevent it for the future. If there's DC interference, whether it's anodic or cathodic present, would be another location to install one. Midpoints between CP test stations are another good location to install one, not only for the AC interference, but because these devices can also check the effectiveness of your DC. Having those test stations at those midpoints, you can see if you're really covered everywhere where you should be. And any time where observations on coupons or soil corrosion probes have exceeded that threshold value, definitely install a test station there. So what is that threshold value? INGA has specified that anything greater than 100 amps per meter squared is a location where you're going to have a problem and you need to mitigate. If the current density is between 20 amps per meter squared and 100 amps per meter squared, you're going to want to keep an eye on it. It's up to you whether or not you install that AC mitigation system, but definitely monitor it because conditions can change. It can jump up above that 100 amps per meter squared, and you want to stay on top of that. Anything less than 20 amps per meter squared is of low threat, so not a huge concern. They further elaborated on this specification. If your DC is less than 1 amp per meter squared and your AC is above 100 amps per meter squared, that's where you definitely have a problem. And also, if your DC is greater than 1 amp per meter squared and your AC is above 30 amps per meter squared, that's where you're going to want to start checking and keeping an eye on things. So whenever you're going out and taking measurements manually using your multimeters, that measurement that you're taking is just a measurement in that point of time. But AC interference is cyclical. So it's going to be cyclical on a daily basis and also seasonally throughout the year. So just to give you an example, this is some information that I pulled from the U.S. Energy Information Administration, which looks at energy demands for the power grid here in Texas. So this was last week when I pulled this information. And you can see that the demand of energy raises up usually in the evenings. Now, why is that? Well, that's because that's when people are going home. You know, people start going home, they start lowering their AC, they're watching their favorite television shows, cooking dinner, using the microwave, opening the fridge 1,000 times to figure out what they want to eat. You know, all of these things are going to consume electricity. So naturally, you're going to see that spike in energy demand between 4 o'clock and 8 o'clock when, you know, things starts to taper down and people start going to sleep. Now, if you're out there going and taking these measurements from your coupon test stations at, you know, 7 in the morning as soon as you get to work, and you're saying, well, nope, there's no AC problems here, you might not be getting the most accurate representation because all of the stuff is happening after you've already left work and have gone home. That's when all of the major issues for AC are happening anyway. And again, so this is here in Texas. You can see that in the winter months, there's less energy demands than in the summer months, naturally, because, you know, the winters here are pretty reasonable. It's not too hot. In the summers, you know, we're pushing 100 for the past few weeks. So, you know, my electricity bill is going through the roof. So you're going to see that more energy demand in the summers than in the winters. And also, it's going to be opposite depending on where you live. In the north, it might be more energy demand in the winters just because you're running your heaters more. So this is something that you're going to want to monitor all of the time consistently. And it's difficult to do if you're going out there and trying to take these measurements manually. So the best thing for you to do is to use remote monitors to capture these measurements. So I'm going to set up a little poll here, and I'm kind of curious if any of you are currently using remote monitors to monitor the threat of AC. So I'm going to launch this poll. Hopefully I get this right. Okay. All right, so the results are coming in. It's pretty split right down the middle. We're looking at 46% yes, 54% no. Wow, 43% yes, 60% no. So kind of looks like based off of the amount of attendees, there's more people who don't have any remote monitoring out there than there is. So it's good that, you know, we're talking about this then, right? Because you can see then the value of having these remote monitors out there. So, all right, looks like everything has stabled off. 44% said yes, 56% said no. All right, so I believe I'm just going to close this poll, and hopefully you guys should be looking at my screen now. All right, so definitely you're going to want to install remote monitors out there to monitor this ACI threat. Now, every organization should have their own strategies out there for keeping on top of this multi-headed monster. This is something that we've outlined as a best practice for you to follow. Using your remote monitors to monitor these coupon test stations to keep track of your ACI threat. And this is a 3-stage approach. So the first stage, you're going to want to capture data frequently because what you're trying to do is to characterize what's happening in a certain region. You're going to use these remote monitors, capture data frequently, and report that data frequently for a period of time. I'm not saying forever. I'm saying maybe from a month to 6 weeks. Once you've kind of characterized what's happening there, then you can turn down the frequency of how much you're measuring on these on the remote monitors. And you're doing this primarily to save data costs and to extend the battery life on these devices because, you know, they're battery powered, they're going to be out there in the middle of nowhere. Generally, there's not going to be line power available, so they're intended to run off of batteries. So that third stage, you're dialing back the measurements even more to extend the battery life even further, because we want these devices to last you several years out in the field before having to change those batteries. So let's look at an example of what a monitoring strategy like this looks like. So in this example, you have the red line denoting that urgent action above 100 amps per meter squared threshold line, which means that you definitely need to take action. You have that gold line at 20 amps per meter squared, which says, okay, this is where I have to kind of keep eye on things. The blue line is your current density for your AC, and then these are measurements taken over a period of a month. Now, you can see that the measurements are cyclical, and it kind of corresponds to that chart that I showed a little bit earlier for the energy demands. So there's definitely a peak time of when that's occurring, and it's happening on a daily basis. So once you've identified what that peak time is, you're going to want to note that down, because that's the time that you're really going to want to focus on taking your measurements. Now, I'm going to give you an insider tip. If you guys are going to be doing this type of stage 1 analysis on your devices, I would say to give us a call so you can adjust your billing plan. We try to save you as much money as possible, so generally you're not going to be taking measurement this frequently. So if you're going to be doing this stage 1, give us a call to increase your data allowance to accommodate for all of these measurements, and that way you don't see any overages on your bill. When you get to stage 2 and you've turned down to your hourly measurements, well, then at that point you can lower your bill again, and you're taking measurements less often now. Now, what we've seen here is in the previous one, a lot of the time it was in that action zone, and some of the times it reached that urgent action. So that meant that we need to install an AC mitigation system here to reduce that AC threat. And so this is what this is showing, that AC mitigation has been installed, and now we're taking our measurements and we see that we're below that 20 amps per meter squared, even at the highest peak that we saw. So we're good here. And we can monitor this for a period of a couple of months just to give us those warm and fuzzies and know that our mitigation system is working as it's supposed to, and our measurements are coming in well below that threshold. At that point, you can transition to the stage 3, and you can turn down your measurements even further to save that battery cost, and you're only taking a daily measurement at that peak time that you've identified. And you can carry on like this throughout the rest of the year. Now, I will say, I would recommend to go back to a stage 1 type of measurement every so often, maybe every 6 months, every year, to recharacterize what's going on in a certain area, because things can change not only on your pipeline system, but they can change on the electric system as well. A new power station may have come on, or maybe they built a new soccer stadium or a new football stadium close by, and now there's a lot more energy that's being demanded off of that grid for a certain area, and your peaks may have changed, or your peak times may have changed. So you always want to keep an eye on what's going on in a certain region. You can use your remote monitors to kind of characterize what's happening on the electric grid if you don't have access to the electric grid data, which is usually not that easy to get a hold of. Yeah, all of this can be generated through our Bullhorn web interface system. We have a variety of reports that can easily help you identify your troublesome spots. This AC monitoring report, for example, shows you a list of all of the units that you have out there, what % of the time they're above that action zone, above that 20 amps per meter squared, what % of the time they're above the 100 amps per meter squared, and quickly see things like this and identify trends and take the appropriate actions for them. Now, this is just one of the reports. The other reports that we have help you drill into those units in more detail, so that you can see exactly what's happening for a certain unit and look at all of the various measurements, or even just see those daily highs if you're capturing hourly data. So with all of this, you've laid the foundation for setting up a comprehensive ACI mitigation program. Now, we realize that you have a lot of assets, and it's not something that you're always going to have the personnel or the time to monitor everything all the time. So definitely set up some structures within your organization to methodically go through all of the units that you have. I believe Andy brought this up in the previous presentation, having a continuous assessment program that consists of a threat assessment, your field verification, your mitigation design, your system installation, and your continuous assessment. It's going to be that cyclical thing. It's going to go all the way around. Set up groups for how you want to monitor all of these different devices, and then tackle, different sections on an annual basis to make sure that you are covering all of the assets that you have out there and making sure that everything is being protected as best as possible. So that concludes our presentation. At this point, we'll leave it up to our Q&A. If you have any questions, I'd be happy to answer. And if we don't have the answers right now, then we'll definitely get back to you.
Hey, Alex, this is Andy. Great presentation. Thank you. We do have some questions that are coming in. If you don't mind, I'll read them out and answer the ones I can and defer to you where I can't.
Perfect.
All right. First question, what about the transposition of HV lines? I think the timing of the question came in just before you addressed the transposition. So yes, when the electrical lines roll and they rotate and they roll them, that is a point of concern, an area of concern where you'd want to see a change in your EMF, and then that would induce a voltage potential, a difference in your voltage potential on your pipeline. And of course, when you have a different voltage potentials, what happens? Current starts flowing. So right there where you see a roll in the electrical line, that's definitely where you'd want to put in a remote monitoring unit. Second question here, has the current density threshold changed to 30 amps per meter squared instead of 20 amps per meter squared?
It depends on which report you're looking at. So if you look at INGA, it has a 20 amps per meter squared. I believe NACE had 20. If you look at the European reports, there's 30. And I don't recall if it changed in 24.
Yeah, exactly.
I believe it's 20 for NACE.
Yeah, the INGA report came out first. They do reference the European standard, and the European standard does do the 30 amps per meter squared, but they settled on 20 amps per meter squared. And then when NACE came out about a year later, the SP report came out a year later, they incorporated the European standard with the 30 amps. I will say that with the customers that I've dealt with, those are guidelines. Each company will sit down and have their own guidelines as well about what's an acceptable level or acceptable criteria for AC current density. So while those are industry standards, your corrosion group may come up with their own internal policies as well. Second question, third question, can the AC coupon corrode showing an increasing current density over time? I'm not sure I'm in a position to answer that one.
Yeah, so the coupon, and especially that image that we showed, did have some surface rust, right? It's not, so that coupon is going to simulate the conditions that are on at that location, right? So the one where you would install your CP, you're not going to have that corrosion. And they generally are set up to have a very long lifetime, I believe up to 30 years. So any corrosion that you do have on that coupon is not going to affect the readings that you're getting off of it. So it's not a cause for concern that you need to worry about too much.
Perfect, thank you. Fourth question here, why don't you use ER probes? We certainly could use ER probes, but that's just not part of our product suite, right? Alex, I'm not
that is, yeah, so we do have solutions for ER probes, and that is definitely something that our customers are using, and it just depends, right? So for the purposes of this presentation, we're focusing more on those AC tools. ER probes is just another strategy that you can use to monitor what's going on in an area, and definitely whatever resources you have available to you and you can utilize, by all means. ER probes is a definite tool that you can use, and yeah, it is something that we utilize as well.
Yeah, I was at a NACE chapter meeting here in Denver last year, a presentation on ER probes. I'd have to go back and pull it up, but there were some pros and cons with ER probes. I don't remember exactly what it was, but I think the conclusion at the end of that NACE chapter was that your native coupons would give you a more realistic, accurate readings over time up there. Let's see, let's go back to next question I see here. What is the recommended coupon size to measure AC current density?
So that's going to be definitely 1 centimeter squared.
Right. Yep. And that's definitely called out in the guide and in the reports as well. Next question, couldn't you just increase the CP? So I guess you're increasing CP on your system to mitigate the growth of the holiday. That's true, but the holiday exists, and therefore that AC current density is looking to discharge, and it's magnified at that very small holiday out there. So CP might be an effective way to mitigate it, but you're not gonna completely get rid of the effects of AC interference out there. Yep, good note here for a good question a comment from William. I just wanted to mention that we've had coupons that had corrosion right out of the bag. Be sure to clean them prior to installation.
Yep.
They're there. And that's it for our questions. Thank you everyone for submitting your questions. I think we're running out of time. Alex, I'm going to migrate to the next one and we'll wrap this up. So 4 webinars giving you a definition of the problem, giving you some weapons in your armory, tools in your toolkits to address this, to tame this multi-headed monster that you'll never be able to slay. Gave you a strategy for allocating your resources on a risk-based approach, and then a monitoring strategy for keeping tabs on this monster that you will never, ever be able to slay. We started this journey at AI about 2.5 years ago, actually, with some presentations internally, and then did some circuits and some tours and did some presentations at Houston, Pittsburgh, Denver. Great turnout at all these. This is a culmination, this webinar series is a culmination of that effort. I want to say thank you to my colleagues at American Innovations, my colleagues at Bass Engineering. We worked really hard to bring this solution to the market. And I also want to say thank you to all of our customers and all of the operators out there in the field taking the time to join us and talk to them. So for those of you who attended all 4 sessions, you get a cap. Let us, I think we're tracking who attended. We'll reach out to you, find out which cap you want. I actually, while the Bass Engineering guys are not here, I'm going to plug American Innovations. I have a bet with the Bass guys that more people will ask for American Innovation hat than they will for the Bass hat. And if I win, I get a steak dinner. So plugging the Bass or the AI hats. But by all means, the Bass guys deserve their fair share of recognition as well. Thank you, everyone. It's been a great journey. If you have any questions, if you want to talk with us further, we'd love to chat with you. We'd love to come on site and do this presentation, repeat this webinar for you. It takes about 4 hours for us to get through the entire presentation. We'd love to come on site and present this to your integrity group, to your corrosion group as well. Let us know. We'd be happy to come on site and meet face to face. Thank you, everyone. Be safe out there. Take care.